Hi, everybody. Welcome to the Mojave Desert, about 20 minutes, a little bit north and east of the city that never sleeps. And one thing we know about a desert winter, oftentimes the winds don't sleep, or as a matter of fact, do the temperatures. They are downright brisk. It is really windy here at Las Vegas Motor Speedway as the Indy Autonomous Challenge returns to a prime position with the CES, the Consumer Electronics Show. And, of course, these robots are going to be putting on a remarkable show of their own right here at Las Vegas Motor Speedway. Again, these are full-on Indy Next cars with tremendous speed potential. But you'll look in those cockpits, there is no helmet, no driver. It is all electronics. And that is what makes the Indy Autonomous Challenge so very special. From the California Institute of Technology, Cast Racer. That is the team that actually makes the car do what it does, but with no driver behind the wheel. It is all done through coding. And once the car, and this is key, once the car starts its run, there is no signaling that can come from the pits other than when you have to make a mandatory speed increase to the next level in one of the competitions. They can simply say, hit the code and go, okay, pick up 10 miles an hour. But the rest is done by the cars, and we'll be explaining that a little bit more as we get ready to go. But with that, it's time for me to get it back down. In just a minute here, we are going to get this one going. But getting back to what I was saying is, the coding is all done. And in the cockpit of these cars, there is all kinds of high-tech autonomous robotic technology, radar, LiDAR, super high-end GPS and GNSS that all comes together along with optics that will help the car make its own decisions on how to drive around the track. Now, they can program in a sort of a line sequence and tell the car this is where you want to pursue, but it's all done through the coding. And we're going to see how that plays out right now. It is time to head back down to Shea Adam for that most famous command in motorsports.
Ladies and gentlemen, start your software.
That's a unique call, probably unique only to the Indy Autonomous Challenge. And here at Las Vegas Motor Speedway, this is what in NASCAR parlance would be a medium super speedway. Really quick, but not as long as, say, the 2.5 miles at Daytona or 2 miles. This one is a little bit shorter, but it still has remarkable speeds. And look at the banking back there. When we were at Indy, nowhere near this level of banking. And this is a true tri-oval. You have turns 1 and 2, which is really one long corner, then the back chute, then turns 3 and 4, which is one long corner, and then you come up into the tri-oval section of the track. And this is a little bit different, but again, a lot of these teams have been here before, but they're dealing with 22 degrees of banking in these turns, 9 degrees of banking through the tri-oval and down the back stretch. And they are going to have to be mindful of this wind. And what the wind does, if you're not familiar with aerodynamics on a car, it is basically what it does is it generates downforce. The wings, the underbody of the car are like an upside down airplane wing. And as you build speed, it pushes it down onto the track. But if you're into a headwind, it speeds that up a little bit so the car has a lot more downforce or stick, but it also creates drag, so it's slower in a straight line. Conversely, if you have a tailwind into the corner, you lose some of that downforce. You're going to have a lot more straight line speed, but the cars have to, through their coding, and look at that, setting off under its own power, our first car. And that's the Caltech machine making its way out. And again, the teams decided who was going to run each discipline. If you decided to run the speed challenge, that is where you will run. Then you won't be doing the passing challenge or the exhibition race challenge. But the cars have to keep into account not just what they're seeing visually and with the LiDAR and the radar and all of that info about where they are on the track, and what pattern to use through the turns, coming onto the straights, through the tri-oval, they also have to be measuring wind speeds and note, okay, we've got a headwind. We're not going to have the top end, but we can maybe go a little bit deeper into the corner before we have to bleed off some speed. Conversely, if you're heading into a turn with a tailwind, you're going to be going a bit quicker than you normally would, so you have to get rid of some of that speed just a little bit sooner. But that's what this whole idea of the Indy Autonomous Challenge is. The challenge is the key word there. It is challenging these students and their staff directors to continue to develop and hone this autonomous technology that allows these cars to go and do this on their own. And there are some people, of course, who will say, well, why would you do this? We like the idea of the drivers in the cars. That's what, makes it exciting. Well, this is not here to replace racing, but what it is here is there's no place like a racing setting to speed up the development of technology that can then be applied into road cars. People talk about eventually having, autonomous taxis, that sort of thing, where you just hop in, there's no driver, tell it where to go, it automatically programs it and then does it. Well, it's that sort of thing where this development is going. And of course, it's not just in the automotive world where a lot of the technology they're working on here can apply. It can bleed over into lots of different disciplines. So the Caltech machine out, and again, this is part of the speed challenge. And what it's all about is just to figure out how fast these cars can go. And at a certain point, and believe me, there's there's terabytes of data flowing from the car to the coders and programmers in the pits. And other than basic commands like speed up, slow down, there's nothing else they can do. It's got to be totally autonomous in terms of how the car drives the lap. But there's just massive amounts of data flowing back to those computers. And that's where a lot of the advancement comes, and they can look at it. So then, next opportunity, they can change it up a little bit, make an adjustment for the next competition. And it's also a programming challenge for these students. Yes, they're working on these tremendous robotics, but they are also working on how to improve the coding, how to finesse the coding, make it more efficient, make everything happen quicker so the car can be a little bit more responsive. And you can see for Cast at first lap, just a tick under 90 miles an hour for a first lap. And you can see how chilly it is right now, folks. Look at that right front tire. You can see that little white band. That is called a sticker, and literally it's the sticker that the tire comes with. And on a warmer day, by now that sticker would be absolutely just ground off of the car. But right now the temperatures are down, and yes, there's some sun out, but you can see a lot of the track is in shadow. So the track is unusually cool. And it's a combination of heat and tire pressure that determines grip. And right now, it's just taking a little longer for those stickers to come off. A 100.5 for lap 2. So they are starting to see some speed now. And again, if you watch the Indy coverage, you know that they were running a bit quicker, but one, the track is longer at Indy, and two, there was no wind to speak of at Indy, and it was significantly warmer. We had a little bit of rain, but that just actually brought the track almost into better conditions here. So they're fighting a very heavy wind here and very cool temperatures, but you can see they're almost 120 miles an hour through the corners now. The amazing thing is, look at the lines these cars are driving. And these are full-on Indy Next, or what used to be called Indy Lights category cars. And it's powered by a Honda K24 turbo engine. It makes around 500 horsepower up on boost. The equipment on board consists of radar, LiDAR, as I said, GPS camera systems. And the car is controlled basically with servos that operate all the inputs from throttle to brake to turning. And of course, those servos are told what to do by the computers and the coding. Look at that, 124 miles an hour coming through the final turn and onto the tri-oval. Lap 5, almost 122 miles an hour. So they are dialing this one up. Running in 4th gear, you can see the RPM. And one of the things that you have to have your mind wrapped around when you're doing the coding for a windy day like this is driving into a headwind. You might want to be running a slightly lower gear because you're not going to have that same straight line speed because of the drag from the wind and the downforce. But look at that, now up into gear 5, and immediately the speeds come up, pushing 140 miles an hour. As they pick up that tailwind, they don't need to have that little bit of extra lug, if you will, from the lower gear. They can go to the higher gear and now let the car flow some speed down the backstretch. And there you can see there is a bit of banking. 141 now in the turns. This should be a really quick lap, probably the last one. What do they do when they cross the line? Are they going to better that 122.3? They did, and by a ton. 11 mile an hour improvement. They're up at 133.129 miles an hour. They might just be looking for a little bit more here. That car autonomously is driving a really nice pattern. And when you're running an oval, on a road course, often you talk about the line. But on an oval, sometimes you're talking more about a pattern. When you're up by the outside wall, when you drop down to that inside where that white line is, and then let it flow out. You see a little bit of a break there. And if you on occasion hear the car do a little chirp, and that 8th lap improved by about 0.4 of a mile an hour, but going into a turn, when you see that red brake light come on, sometimes you'll hear this little chirp sound. That's the wastegate on the turbocharger releasing some of the pressure. Because the turbocharger obviously just builds a huge amount of pressure to help build horsepower. And the wastegate, at a certain point, when you lift in a turbo car, you get all the leftover pressure and it'll spike. And if you don't release it, it can be very problematic, and it'll be costly in terms of performance. And think of a balloon that's full of air, and then you grab the nozzle and kind of pull it sideways, and you can make it screech. It's a very simple explanation of what's going on. Air under very high pressure escaping through a rather small orifice will create that kind of a sound here. 144.3 on lap 10. Cast is absolutely flying out here. Watching the throttle, you can see when they throttle, the car will sometimes breathe with a little bit of brake. The longer, obviously, you can maintain that throttle, the quicker your laps are going to be. Let's see, what do they put up this time? Oh, they're knocking on the door of 150 in that straight line. And the interesting thing here about aerodynamics and the wings on the cars and the underbodies on these cars is it isn't very effective until you start to get into some serious speed. And once you get into that serious speed, and it looks like their run is coming to a completion here. But once you get into speed, the car actually will handle better, stick to the ground better, because it is the air moving across those wings and under the car through the diffusers on the exit that makes the car generate more and more downforce, it's called. So 144.323 miles an hour for Cast Racing, and that is a great start to this competition. Fabulous job. I'll tell you what, that's a pretty good target for everybody else to have to try and hit here. And then when the run is completed, different signals go to the car. We should also point out that there are also engineers for each team and up in race control that are watching things, but the race director himself or herself can also send signals to the car like yellow flag, red flag, black flag, and the car is automatically programmed to react in a certain way when those commands are given. Oftentimes it's simply slow down and start making your way back to the pits. Sometimes it's a slow down quickly and stop, depending upon what's happening on the track. So there is a lot that these cars are processing. And think about it, folks. The average speed of 143 miles an hour. Think about how quickly the processing has to happen for this car to be able to do this. And that, to me, is the magic, the mystical aspect of this is the speed of the processing. And you add to that the size of the data. Like I said on that run, terabyte upon terabyte of data was getting fed into the pits. But the car was also utilizing the coding, and with the LiDAR, radar, and all of those components, had to decide on its own what line to drive, when to slow down, when to speed up, and in this case, when to make that turn and wander its way down into pit lane. So what a start. Cast Racing throwing out pretty serious number here. Frankly, I always like to see that happen. I like to see a car come out right out of the gate and put up a really stellar time, because that sort of tells everybody else, all right, you better step it up because we're serious here.
I think their fists were the tightest things ever on the racetrack because everybody was so tense and nervous. You guys survived it, though. Deep sigh of relief. Do you think there was more speed out there in the car?
We'd like to, but sometimes you just you say that look, everything's looking great, we should just run at that, and you come back. It is Vegas. We gambled. We didn't gamble too hard. I think we came back winners from this run. So I think the teams. Thank you very much, team. I think we had a great run. We beat our record by about 20 miles an hour. So that's fast, and we have terrible conditions today being out there. So I am ecstatic. That is better than I could have hoped for.
Congrats to you and the entire team. Great job, guys. Really enjoyed that run.
I love that. It's Vegas. We gambled. And as we were talking about, everybody was concerned, what kind of speeds would we see? And then they beat their record by 20-some miles an hour in these conditions. And that was an absolutely fabulous first ever multi-car racing exhibition to show what is possible with Indy Autonomous Challenge. And as Paul Mitchell said, more to come, going after speed records, road race racing at Monza, so much more. And we're doing it all here. And, of course, I'm sure a number of these teams and team members, when they get everything buttoned up, will be heading right toward that monolith of lights and excitement and energy in Las Vegas. But that wraps up our coverage of the 2025 Indy Autonomous Challenge at the CES, the Consumer Electronics Show here at fabulous Las Vegas and Las Vegas Motor Speedway. Congratulations to all of our teams in the Indy Autonomous Challenge. Congratulations to the organizers of Indy Autonomous Challenge. And a big thank you, as always, to Shea Adam for doing such incredible work down there. And I also want to say a big thanks to Apex Productions for doing the coverage of this absolutely revolutionary and fascinating exercise in technology. I'm Greg Creamer. Thank you so much. And we look forward to having you back again when next Indy Autonomous Challenge takes to the track. We'll see you then.